Let's sum a series. I want to evaluate this series carefully. So the claim here is that the sum k goes from 0 to infinity of 1 over 2 to the k is equal to 2. But what does that even mean? Well, what it really means is this. It means that the sum k goes from 0 to n of 1 over 2 to the k is close to 2 whenever n is big. Right? This sum makes sense because this is just a finite sum. It's just telling me to add up 1 over 2 to the k for the values of k between 0 and n. So this at least makes sense. And what does close to 2 mean? Well, it means as close as you want it to be to 2. And how big does n have to be? Well, it has to be true whenever n is larger than some fixed big value that depends on how close you want the thing to get to 2. Let's say the same thing, but in terms of limits. So more precisely, I'll define the sequence S sub n, the sequence of partial sums, to be the sum k goes from 0 to n of 1 over 2 to the k. And the claim that this series has value 2 just means that this sequence has limit 2. It means that the limit as n approaches infinity of the nth partial sum is 2. How do I evaluate that limit? Well, let's look for a pattern. So S sub 0, well, that's the sum k goes from 0 to 0 of 1 over 2 to the k. So that's just 1 over 2 to the 0, which is just 1. S sub 1, well, that's the sum k goes from 0 to 1 of 1 over 2 to the k. That's 1 plus 1 over 2 to the first power, which is a half. S sub 2, well, that's the sum k goes from 0 to 2 of 1 over 2 to the k. That's 1 plus a half plus 1 over 2 squared, which is a fourth. And I could simplify that a little bit. I could write that as 1 plus 3/4. S sub 3, well, that's the sum k goes from 0 to 3 of 1 over 2 to the k. So that's 1 plus a half plus a fourth plus 1 over 2 to the third, which is an eighth. And I could add a half, a fourth, and an eighth and get 7/8. Then I could compute S sub 4, right? And that'll be 1 plus a half plus a fourth plus an eighth plus a 16th. And that'll be 1 plus 15/16. And now maybe you're beginning to see the beginnings of the pattern here, right? I've got a half, 3/4, 7/8, 15/16 here. So it's perhaps believable, I mean, this isn't a proof, it's just a little bit of evidence, but the pattern is suggesting itself that the nth partial sum is 1 plus, wants to be a number just a little bit less than 1, and it's the corresponding power of 2 in the denominator and 1 less in the numerator. So I could write that as 1 plus 2 to the n minus 1 over 2 to the n. And then I could simplify that a little bit. I could split that up as 1 plus 2 to the n over 2 to the n minus 1 over 2 to the n. And I could write that as 2 minus 1 over 2 to the n. I haven't proved that, but hopefully that formula seems believable. In any case, armed with that formula, we can evaluate the limit. Well, here we go. I want to take the limit of S sub n as n approaches infinity, and now I've got that formula for the nth partial sum. So that's the limit as n approaches infinity of 2 minus 1 over 2 to the n. That's a limit of a difference, which is the difference of the limits, provided the limits exist. So this is the limit just of 2 as n approaches infinity minus the limit of 1 over 2 to the n as n approaches infinity. This is the limit of a constant, which is just that constant, minus, this is the limit of a quotient, but look at what happens here. The denominator is very, very large. I can make the denominator as large as I like, right? 2 to the n can be made very, very positive. 1 over a very large number is very close to 0. So this limit is in fact 0. And that means that the limit of the partial sums is just 2. That means that this series converges to 2. And I can not only see that algebraically by using that limit, but I can also see it geometrically. Geometrically, I can draw a picture like this, where I've got a half, a quarter of the square, an eighth of the square, a 16th of the square, a 32nd of the square, a 64th of the square, and all these pieces fit together to build one unit square. And what that's showing me is that the sum k goes from 1 to infinity of 1 over 2 to the k, well, that really is 1. So the sum k goes from 0 to infinity of 1 over 2 to the k. Well, that's the first term plus all the rest of these terms, so that's 1 plus 1. That must be 2.